Hello, this is Team 15, and I'm here to introduce you to our optimization system, an electric delivery van system. Next slide. Our system itself is the design of a battery pack and motor for an objective of minimizing the cost of energy over 5 years using an optimized route. Our subsystems include the route optimization subsystem, the powertrain subsystem, and the battery pack subsystem. Our system flow diagram boundary is shown below, with the system input being delivery locations and the system output being the cost. Next slide. Our inputs for battery are max power and energy, motor is drive cycle and battery mass, and trip is battery capacity and energy consumption per mile. Our outputs for battery are weight, capacity, and cost, motor, energy per mile, and trip is total distance. Our coupled variables are battery weight and maximum power for battery and motor, energy per mile and drive cycle for motor and route, and lastly, battery capacity for route and battery. Our design variables for the optimization are NS, NP, and cell chemistry, which will directly influence battery weight and capacity. Next slide. The rationale for our system is to address a real-world logistics challenge. As many companies turn towards EVs for deliveries, it is important to optimize the powertrain and battery sizing, allowing the vehicle to not only deliver all of its packages during a route, but reducing the cost per run and minimizing vehicle cost overall. This in turn allows for improved deliveries and cost savings for the logistics companies, resulting in reduced costs for the end customer. Next slide.
Yeah, so I'll be walking through our optimization model for electric delivery van. The goal is to optimize a cost-effective and energy-efficient system using holistic optimization approach. This slide shows our main objective function. We want to minimize the total cost of owning and operating the battery over 5 years. Our cost includes two parts. First is like the energy consumption, cost over the battery's life, and the upfront battery pack cost. The key variables include the number of battery cells in series and parallel, the route taken, the motor weight, and the efficiency of the motor. Next slide. Here are the system parameters used in the optimization. On the left-hand side, we have constants like electricity cost, vehicle lifespan, number of operating days, and physical values like tire radius and frontal area. On the right-hand side, we have like mechanical parameters like rolling resistance, drive ratios, and efficiency. These values help define the vehicle behavior and are used in our energy and cost calculations. Next slide, please. Now let's look at the constants and variables. The constants ensure the system is realistic and safe. For example, the total route time must be 8 hours and it has been taken from the fact that the driver will be operating 8 hours a day. The battery must not exceed a voltage and capacity limit. The total vehicle weight must not uh, exceed 9,500 pounds, and motor efficiency and motor mass are within the real system limit. We also define variables domains for number of cells and motor specs. Intermediate variables like vehicle power, battery mass are calculated during the optimization process. Next slide. Next, please. This is the list of 20 cell candidates. We considered each has different values for voltage, capacity, peak current, weight, and cost. We run the optimization for each candidate to find the best overall combination for the system. Next slide, please. Here is the big picture. We divided the model into three subsystems, root, motor, and battery. Each subsystem can be optimized individually, but for the best result, we also perform full system optimization. This links all the subsystems together. We optimize three main design variables, number of series cells, number of parallel cells, and the battery candidate. The full system optimization ensures all subsystems work together to minimize the total cost over 5 years.
The trade-offs in our system include the balance between mass and energy consumption energy consumption and cost, and the battery capacity and route cost. For example, increasing the vehicle mass will increase the energy consumption, but increasing the vehicle mass allows for larger battery and more range. Increasing energy consumption can allow for a faster trip, but at greater cost. And increasing the battery capacity can allow for fewer recharging detours at the expense of battery cost. Next slide. Our optimization approach was to identify the linked variables in the subsystem models, simultaneously solve for the shared variables, and feed this into the system-level objective function. The assumptions included constant electricity costs, no vehicle maintenance costs, no battery capacity paid, and a constant vehicle mass in spite of deliveries. Next slide. The system includes models for route, battery, and motor subsystems. The route is modeled as a digraph where vertices represent charging stations and delivery locations. Edges represent connecting routes, and the battery is modeled as a single pack with a mass and a capacity that is derived from a number of cells in series and parallel. Next slide. The powertrain is modeled as a single AC electric motor and a gearbox with a drive cycle that governs the motor power demand. Energy loss coefficients are used for the gearbox aerodynamics and rolling resistance. Next slide. The system-level optimization model that we have selected is the genetic algorithm. This is selected over gradient-based techniques due to our nonlinear and discontinuous objective function. At the subsystem level, we use a genetic algorithm for the motor optimization and battery optimization, while we use simulated annealing for the route optimization. Next slide.
So we run our system level optimization with 10 iteration each and varies the constraint and parameters that listed in this table. And here we take the base case as mentioned in the first row, and the variations of parameters and also constraint will be further discussed in sensitivity analysis. Next. So based on the results and to see if our system is comparable with real EV delivery van, we took two commercially available delivery van example, like Ford e-Trans and also Rivian EDV, and we'll compare their life cycle cost over 5 year and energy consumption rate with our design delivery van. And please note that here we assume the battery pack cost will take up to 40% of the overall vehicle price. Next. So for simplicity, we assume that daily range of all vehicle type is the same. And we can see that our battery capacity and energy consumption rate are pretty much comparable with Rivian and also Ford with 91.3 kilowatt hour and also 0.57 kilowatt hour per mile. And also with the total cost over 5 year life cycle is relatively low compared with the other two. Next.
So in the sensitivity analysis, we pick 4 different parameters and 3 different constraints, and then analyze how they will influence our optimization. Next slide. So the first one will be the lifespan parameter. So the cost will be increased as the lifespan increases as we expected. Next slide. And then here is the mass. Actually, the cost doesn't have changed a lot since we did not include some of the mass assumption. Next slide. And then here is the route distance. As we can see that this have a significant impact on our cost, which means you drive more, you will cost more on energy. Next slide. So here is the charging power. Actually, the charge power is not so sensitive. Next slide. And here is the time limit. We can see that the cost will remain constant, even have different time limit. Next slide. And here is the energy constraint sensitivity. Since this will determine our battery capacity, we can see it will increase as the cost will increase as the constraint increased. Next slide. And then this is the minimum voltage constraint, and we also did a sensitivity analysis for that. And next slide is our summary. So we normalize the value and then calculate the difference on cost. We find out the most sensitive parameter is the road distance, and then the most sensitive constraint will be the energy constraint. Next slide.
Okay, coming to the comparison of subsystem results to system results, we see that NS and NP from battery subsystem have increased for the global system optimization, and the energy consumption for route subsystem has decreased by 3 units, and change in motor weight for motor subsystem has marginally changed, and the vehicle weight for motor subsystem has decreased by 250 kgs. Now, discussing the results, we see that our design is comparable with commercially available EV delivery vans in terms of specification and cost. Seeing the sensitivity analysis, it is confirmed that total cost is being sensitive to battery capacity, maximum daily time operation, and distance. If we look at the improvements which can be made into this model, we can take account the time and location dependent electricity rate. We can include battery and powertrain maintenance costs. We can consider the effect of battery capacity degradation on the charge based on the charging frequency and the route time and energy. And we can consider a trade-off between the cargo mass and powertrain mass in the total vehicle mass. And in this case, we have considered that battery will be used for the span of 5 years, and we have considered that it runs for 5 years irrespective of distance driven. So we can consider to add that complexity to the model for more realistic cost analysis, where we consider that there will be a change of battery within the span of 5 years. Thank you. Okay.